So let's see. Somebody is having. Okay, fine, no problem in that. Somebody is asking me that he'll be able to join late, no problems. So students, the contents that we are going to cover today include the following. Okay, so let's get started. See, right from class 1, we have been saying that whatever mechanical properties any metal or an alloy system is showing to you under some given conditions of pressure, temperature, composition, or any other parameters, these mechanical properties which the material is showing to you depends upon the microstructure that material. No, the screen has already been shared, Manoj. There are still students who are entering. I can only request that be on time, please. It wastes your time only. Okay, I'll again share it. Is the screen visible now? Students, is the screen now visible? Okay, thank you. I received your messages. Thank you so much. So students, in today's class, we'll try to cover as to what is meant by microstructure present in a material system. Is this slide visible where I have written the mechanical properties which any metal alloy system possesses? Is this visible to you? Okay, thank you. So students, I was saying that whatever mechanical properties any material system is showing to you is showing because under those conditions your material system possesses some specific microstructure. So in today's session, we'll try to understand as to what is meant by this term called microstructure for a material system, especially for a metallic system. Okay, now the same thing has been written in the second bullet point also, that if some metal system, alloy system is showing some specific mechanical properties, it is because it has got some peculiar microstructure present in it. For example, if a mild steel specimen held by you at room temperature conditions is showing you very good ductility and moderate strength, whereas cast iron is showing you exceptional compressive strength but very poor tensile strength and very poor ductility, it means that this mild steel sample and this cast iron samples have got some peculiar microstructures present in them, and these microstructures are very different from each other. That is why these two samples are showing very diverse different properties to you. Okay, then this also means that if you want to change the mechanical properties of a material system, for example, you are not happy that why this mild steel sample is having only moderate strength, why not it is having exceptionally high strength. So if you wish to bring a change in the properties of a metal system, you will have to bring about a change in its microstructure. Fine. So, okay. So we must know that which particular microstructure provides what particular set of mechanical properties. See, this knowledge is important. If you wish to have control over the mechanical properties of a material system, first of all, you should know that which type of microstructure results in which type of properties. And then secondly, students, you must know that what type of processing which type of processing route would get me that peculiar microstructure which I am desiring for, and hence desirable properties in a metal system. So you need to know two things. You need to know that what type of a microstructure would give what type of mechanical properties, and then you should know or should have knowledge that what is the processing route to be followed for a metal or an alloy system to get desirable microstructure and hence mechanical properties present in it. And students, if you know these two things, which I have written down over here as 1 and 2, you can have total control over the mechanical properties of a metal or an alloy system. And that is what exactly industrial metallurgy tries to equip you with. Industrial metallurgy would tell you that why a particular microstructure is giving a particular set of mechanical properties in a metal system. Industrial metallurgy or physical metallurgy would only explain to you that what microstructure is needed to bring about some desirable mechanical properties present in a material system. And it's industrial metallurgy or physical metallurgy only which tells you that what type of processing has to be given to the material system in order to get a desirable microstructure and hence mechanical properties in a metal or an alloy system. So in the nutshell, industrial metallurgy or physical metallurgy is a field which would help you in equipping yourselves with that complete knowledge with which you can have total control over the mechanical properties of a material system. For your reference, students, I am again explaining that any property of a material system, in order to determine the magnitude of that property, if you have to apply a load or a stress on the material, and the response of the material under that load or stress tells you about the magnitude of the property that you are trying to determine, any such property is a mechanical property. So what's a mechanical property? Mechanical property is a property whose magnitude depends upon the response to the load or the stress applied to a material. For example, hardness, you provide a point load and the material under the effect of that point load indents. And then a material which indents more gives less resistance to indentation, possesses low hardness. The other material which gives more resistance to indentation possesses more hardness. Similarly, strength, the resistance to deformation under external gradual load, impact strength, the resistance to fracture under sudden or jerky or instant load. So any ductility, the amount of plastic deformation which a material suffers on the application of external gradual load. So any property for which determining the magnitude of that property, you have to put a load or stress over the material, and the material's behavior under that stress or load gets you that property. Any such property is called a mechanical property. And generally in mechanical engineering field, the other set of properties, students, are called physical properties, like refractive index of the glass, density of a material, volume of the material, specific heat, electrical conductivity. All these other properties where you do not have to apply load or stress over a material in order to determine the properties of a material, any such property is termed as a physical property. Please mind it, in physical metallurgy, that is industrial metallurgy, we are only bothered about the mechanical properties of a material system. Whatsoever we are trying to control are mechanical properties. Physical properties may or may not get affected when you are trying to change the microstructure and hence the mechanical properties. I hope this is clear. Okay, so let's move forward. So if you know answers to the above two key points, we can learn to have total control over the mechanical properties of a metal or a material system. And this is where industrial metallurgy, or what is called also as physical metallurgy, comes to our help. Okay, students. Then what is the meaning of this term microstructure? So in the nutshell, what are we trying to say? We are trying to say that whatsoever mechanical properties are existing in a material system are existing because the material has got some peculiar microstructure. And if you have to change the mechanical properties of a material system, you'll have to change the microstructure. So what do you do in physical metallurgy or industrial metallurgy? You learn to manipulate this microstructure, students. But before we start learning how to make changes in this microstructure or how to make manipulations in this microstructure, we must be knowing as to what is meant by this term. what all makes up the microstructure of a metallic system. So this I've already said. So microstructure is the micro scale structure of a metal or an alloy, generally revealed for its prepared surface. It would only get revealed when you have metallurgically prepared the surface through grinding, followed by polishing, then by etching through a chemical reagent. So when this prepared surface is looked at on microscopic scale through an optical or electron microscope, we get to see what is termed as microstructure of the material. So microstructure of a materials system is the micro scale structure of the material system, which is revealed generally for its prepared surface through these microscopes. Optical microscope is there, scanning electron microscope is there, transmission electron microscope is there, etc., etc. Okay, so then let's see, let's give a more complete definition of this term, and students, you can go through it. Students, when we have captured the microstructure of a material system through an optical microscope or a SEM or a TEM, we call that microscope as a micrograph, right? For example, when you have clicked your image, we call it a photograph. Similarly, microstructure, when it has been clicked and we are discussing the image captured, we refer it to as the micrograph. Some queries coming, let me see. Yes, that can be discussed. I'll try to prepare some slides on that how do we actually determine the microstructure, right? Or I'll show some video to you. Let me prepare that. Give me some days for that. Okay, thank you. So we were discussing this definition. Microstructure of a metal or an alloy system is a micrograph which shows the shape, size, distribution of the various phases which are present in a particular grain size in a metallic system when its prepared surface is viewed under an microscope. Bacho, if you look at this definition carefully, you would be able to realize the two main components which make up the microstructure of a metal or an alloy system. When you look into the microstructure of a material system, or when you view the micrograph of a metallic or an alloy system, one, you would see different phases present in it. There might be only one phase present. There might be different phases present in it. So one of the things which makes up the microstructure of a material system are the phase details. What type of phases are present? In what number are they present? How much of volume or space of the microstructure each of the phases has occupied? What is the shape? What is the size? What type of distribution each of the phases is having in the microstructure of the material system? And so one important thing which makes up the microstructure is the phases and their details. And the other important aspect is the grain size. So if you look at this definition, you will see both the things present: details of various phases and particular grain size. So microstructure has got two major components present in it. One is the phase details, and other is that these phases are present in what type of a grain size. Are there only 4 grains? Are there 40,000 grains per unit space? So grain size is another very important constituent which makes up the microstructure of a material system. And I'll try to show both these types of both these constituents would be seen in the examples that I'll try to illustrate in front of you in just a while. Okay. So as I said, microstructure of a metals or an alloy system makes up is made up of two major components. One is the grain size details, and there are different meanings which are associated with grain size details. There are different ways how grain size can be expressed. You can use any of the forms. You can talk about grain size in terms of the average distance between the grain boundaries, which are seen in the microstructure. You can talk about the number of grains that are being observed per unit space or volume. You can assume the grains to be spherical in shape, and then you can talk about grain size in terms of the average grain diameter, or you can use indices like the grain size number, the grain size index, etc., etc. But generally, how will you talk about grain size? Sir, relatively fine grained structure is being seen. So relatively coarse grained structure is being seen, etc., etc. Right. So the other major thing that is present in the microstructure of a material is the phase details. How many phases are present? What is the type of each phase that is present? What is the volume fraction that is present of each phase in the microstructure? What type of shape? What type of size? What type of distribution each phase? What is this shape, size, distribution is given a common name, morphology. Morph means different structures. This is a Greek word. So morphology of each shape, morphology of each phase means what type of shape each phase is having. Is the phase plate-like? Is the phase needle type? Is the phase appearing to be globular? Is the phase appearing to be pin type? So the phases can have different types of shapes, and every type of shape would give you or would influence the mechanical properties that are being observed in a material system. For example, if you have very thin needles, ductility would never be good. If you have very thin needles, impact strength would never be good. So if your impact strength of the material is poor, you'll have to change the shape of the phases. So each of these things, students, each of these things that are being shown on this slide make up the microstructure of a material system. And by some processing, if you change any one or more of these things, the microstructure would change, and as such the mechanical properties of a metallic system would change. So what do you try to do in physical metallurgy or industrial metallurgy? First of all, you try to see that how does microstructure of a material system affect the mechanical properties of a material system. Means why a particular type of a mechanical properties are given by a particular type of a microstructure, or how do each of these constituents of the microstructure, how do they affect the mechanical properties of a material system, you try to learn in physical metallurgy. And once student you have learned that which microstructure gives what type of mechanical properties, then you have to know that what type of processing can give me a particular type of a microstructure. अगर आपको ये पता लग जाए कि कौन सा माइक्रोस्ट्रक्चर क्या मैकेनिकल प्रॉपर्टीज दे सकता है, और दूसरा फिर आपको ये पता लग जाए कि जो माइक्रोस्ट्रक्चर जो मैकेनिकल प्रॉपर्टीज दे सकता है किस तरह की प्रोसेसिंग कर वो वाला माइक्रोस्ट्रक्चर मैं मटेरियल में ला सकता हूं, you can have total control over the mechanical properties of a metals or an alloy systems. And this is what you learn in industrial metallurgy, in physical metallurgy. I hope I'm clear till here, or if you have any questions, please ask. Then I'll move forward. Very quickly, if even 4 or 5 students will answer that, yes, sir, it's clear, I can move forward with a lot of confidence then. I'm waiting for others to respond. Okay, students, thank you so much. So let's move forward. Now, this is one schematic of a microstructure of a typical metallic system, through which again I'm trying to explain this term microstructure to you. And then in the remaining slides, I would cover that different microstructures, how they can be different from each other, so that it gives you a better idea as to what is meant by microstructure, how different microstructures can be there. And in the next session, we'll cover as to how do constituents of the microstructure influence or change or affect the mechanical properties of a metallic system. So that would be interesting. So students, here you can see the first thing that you should see is that what type of a grain size is there. But for that, you should know that because we are talking about a metallic system, we have grains. So here grains, or what are also called crystals, which have a definite crystalline structure for them. So this region 1 is a grain, this region 2 is a grain, this region 3 is a grain, this region 4 is a grain, and they are separated by what are called grain boundaries. We'll also devote a session to understand actually how do these grain boundaries form, how do these grains form. But as for now, you believe me that these regions, what are shown in white and red, they are clearly crystalline. And as these regions were getting formed initially, when they grew up, when they were growing, when grain 1 was growing, grain 2 was also growing. And somewhere over here in the black region, these two grains collided because their growth was complete and their growth was now obstructed by the adjoining grain. So this region which is being shown in black is not a crystalline region. This is rather an amorphous region. And this is at the boundaries of the grains. So this region is called grain boundaries. So this entire black region is the grain boundary region, which I have labeled over here. Now, so what you will see that 1, 2, 3, 4. There are 4 grains or 4 crystals, and they are quite big in size. And if you take the average distance between the grain boundaries, the grain size that would be calculated would be a relatively coarse grain size. Or if you assume each of these grains as spherical, and if you find out their average diameter, and if you take average diameter of each grain and then you take the average of all those averages, you can find out the average grain diameter, which would again be called the grain size. So there are different methods how grain size can be calculated, students. You can also talk about that when you look into under the optical microscope at 100x per square mm, how many number of grains you could see. This is another method of expressing. This is another method of expressing the grain size, right? So there are different methods which in times to come we'll discuss in the class. So one aspect of this microstructure is what type of a grain size is there. And from my experience, and you can also visualize that relatively coarse grains are there because there are very few grains present in the total space. Had it been say 1000 grains over here, we would have said, sir, the grain size is fine, the grain size is small, we have a relatively fine grain size, but here we have a relatively coarse grain size, right, students? So no, somebody is asking, does that mean 4 different phases? 1, 2, 3, 4. No, फेजेस की डेफिनेशन याद रखिए. फेज का मतलब है कोई भी ऐसी रीजन जहां पर केमिकल कॉम्पोजिशन, फिजिकल स्टेट, क्रिस्टल स्ट्रक्चर, लेटेस्ट डायमेंशंस, ये चारों चीजें सेम हैं. तो स्टूडेंट्स अगर आप इस माइक्रोग्राफ को देखोगे, इफ यू लुक एट दिस माइक्रोग्राफ, let us assume that when I investigate this white region, this entire white region, whether it is in grain 1 or 2 or 3 or 4, this entire white region has only got one chemical composition, one physical state, one crystal structure, one lattice dimension. So this entire white region, irrespective of the fact in which grain it is present, it is representing a single phase. And here I've said that let this phase be called white phase, white portion, or ferrite phase. Similarly, students, when I investigate this second region which is appearing red in color, because the color is different, मेरे दिमाग में शक आ जाना चाहिए कि भाई ये वो फेज नहीं हो सकता जो व्हाइट था. पर मैंने कहा था कलर चेंज इज नॉट ए श्योरिटी, इट्स ओनली अ अलार्म बेल कि यार ये जो रीजन आपको माइक्रोग्राफ में या माइक्रोस्ट्रक्चर में नजर आ रही है, प्लीज इन्वेस्टिगेट करो क्या वो 4 चीजें इस रेड रीजन में भी वही हैं, क्रिस्टल स्ट्रक्चर, लेटेस्ट डायमेंशंस, केमिकल कॉम्पोजिशन, फिजिकल स्टेट जो व्हाइट रीजन में है. बच्चों जब आप इन्वेस्टिगेट करते हो आप देखते हो कि 4 में से एक या एक से ज्यादा चीजें डिफरेंट हैं, तो आप कहोगे कि सर ये रेड रीजन जो है ये फेराइट फेज या व्हाइट फेज नहीं है, ये तो कुछ और है. और फिर आप इन्वेस्टिगेट करोगे कि ये जो रेड फेज था और ये जो रेड फेज दिख रहा है, ये जो रेड फेज दिख रहा है, क्या इन चारों रीजन्स में वो चारों चीजें सेम है? सपोज करिए सेम है, तो ये 4 डिफरेंट रेड रीजन्स भी कोई एक पर्टिकुलर फेज है. आई एम कॉलिंग दैट फेज एज द रेड फेज और द सीमेंटाइट फेज. तो अगर आपसे इस माइक्रोस्ट्रक्चर के बारे में कोई पूछता है तो आपका जो क्वालिटेटिव आंसर आएगा, क्वांटिटेटिव तो तब आएगा अगर आप ग्रेन साइज को एक्चुअली मेजर करो किसी न्यूमेरिकल मेथड से, जो कि हम आने वाली क्लासेस में डिस्कस करेंगे. लेकिन यहाँ आपका आंसर आएगा कि सर रिलेटिवली कोर्स ग्रेन स्ट्रक्चर है और उसमें सर दो फेजेस प्रेजेंट हैं सर। एक फेज है वाइट फेज, फेराइट फेज है वो सर। दूसरा फेज है रेड फेज, वो सीमेंटाइट फेज है सर। फेराइट फेज ने ज्यादा वॉल्यूम ले रखी है, आप देखें 96-97% जगह जो है वो ले रखी है सर फेराइट फेज ने। तो वॉल्यूम फ्रैक्शन ऑफ फेराइट फेज इज अबाउट 96% सर। सीमेंटाइट सिर्फ 4% है सर। फेराइट की अगर आप मॉर्फोलॉजी की बात करें, वो बैकग्राउंड फेज है सर, उसकी कोई शेप नहीं है, वो मैट्रिक्स बना हुआ है, वो बैकग्राउंड में पड़ा हुआ है। और सीमेंटाइट फेज जो है सर वो थिन प्लेट्स की फॉर्म में है। तो बच्चों दिस इज व्हाट यू कैन टेल अबाउट द माइक्रोस्ट्रक्चर एट द वेरी फर्स्ट ग्लैंस। बट द आइडिया हियर वाज जस्ट टू टेल यू दैट व्हाट डज माइक्रोस्ट्रक्चर मीन एंड व्हाट डज माइक्रोस्ट्रक्चर कंप्राइज ऑफ। इट मेनली कंप्राइजेस ऑफ टू थिंग्स। किस तरह का ग्रेन साइज है, फाइन है कि कोर्स है, उसको हम आगे चलकर क्वांटिटेटिवली एक्सप्रेस करना भी सीख जाएंगे। यहां हमने क्वालिटेटिव टर्म्स में कह दिया कि रिलेटिवली कोर्स ग्रेन सा माइक्रोस्ट्रक्चर नजर आ रहा है। और दूसरी चीज हम कह सकते हैं कि सर ग्रेन्स कितने हैं, दो। क्या टाइप है सर, एक फेराइट है, दूसरी सीमेंटाइट है। मॉर्फोलॉजी सर फेराइट बैकग्राउंड फेज है, उसकी शेप की बात करने की कोई महत्व नहीं है क्योंकि वो तो पूरे ग्राउंड में बिछा पड़ा है। हाँ सर सीमेंटाइट फेज जो है वो थिन सी प्लेट्स की फॉर्म में पड़ा हुआ है सर। वॉल्यूम फ्रैक्शन फेराइट का बहुत ज्यादा है, तकरीबन 95-96% जगह जो है माइक्रोस्ट्रक्चर की वो फेराइट फेज ने ऑक्यूपाई कर रखी है। तकरीबन 4-5% जगह जो है वो सीमेंटाइट फेज ने ऑक्यूपाई कर रखी है। सो स्टूडेंट्स दिस इज ऑल अबाउट द माइक्रोस्ट्रक्चर ऑफ दिस metal or an alloy system. I have a couple of queries which sir is this the sir why is red scattered? Somebody is asking why is the red phase scattered? बच्चों हमेशा ही मेटेलिक सिस्टम्स में ऐसा होगा कि एक कोई फेज होगा जो सारी जगह बिछ गया है, जिसकी वॉल्यूम फ्रैक्शन ज्यादा है, और दूसरे जो फेजेस हैं वो डिस्ट्रीब्यूटेड हैं इस तरह से। फिर किसी ने पूछा है इज दिस द स्कीमेटिक फॉर एवरी मेटेलिक सिस्टम? नो 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 नो। metallic systems will have different types of metallic systems, would depend upon उनकी composition क्या है और आपने उनको कैसे प्रोसेस किया है। मैं आपको अभी दिखाऊंगा भी कई metallic systems के microstructures। somebody is asking is this a single phase? देखिए भाई जो टोटल माइक्रोस्ट्रक्चर मैं आपको यहाँ दिखा रहा हूँ ये 2 फेज रीजन है। इसमें एक फेज है ये व्हाइट रीजन, तो ये सारा व्हाइट पोर्शन ये एक ही कोई फेज है, नाम है फेराइट फेज। और जो ये रेड है ये चाहे अलग अलग जगह पड़ा हुआ है लेकिन ये फेज एक ही है, तो ये है रेड फेज या सीमेंटाइट फेज। तो दिस माइक्रोस्ट्रक्चर कंप्राइजेस ऑफ 2 phases, one phase is ferrite, the other phase is cementite. I hope I have answered it. देखिए मानव is asking that grain boundary is made up of amorphous material. No, grain boundary is not made up of amorphous material. Grain boundary भाई उन्हीं चीजों की बनी हुई है जिसके ग्रेन्स बने हुए थे, लेकिन जब लिक्विड स्टेट से ग्रेन्स ग्रो कर रहे थे जब तक तो वो एक दूसरे से नहीं टकरा रहे थे, वो ग्रो कर रहे थे, उनके अंदर सब कुछ बिल्कुल क्रिस्टलाइन था। लेकिन बच्चों ध्यान दो, सपोज करो 3 ग्रेन्स थे सिस्टम में जब ये पूरा लिक्विड था, 3 जगह सॉलिडिफिकेशन शुरू हुई, 3 जगह सॉलिड फेज फैलना शुरू हो गया। जब तक वो इंडिपेंडेंटली लिक्विड स्टेट में फैल रहा है उसके अंदर जितनी भी चीज है वो सारी क्रिस्टलाइन है, कोई खास डेफिनेट क्रिस्टल स्ट्रक्चर है। लेकिन आप देखिए एक स्टेज आएगी जब ग्रो करते करते ये जो तीनों सॉलिड्स हैं इनके जो बाउंड्रीज हैं वो एक दूसरे से टकराएंगी, और जब टकराएंगी तभी सॉलिडिफिकेशन कंप्लीट होगी। लेकिन जहां ये टकराएंगी, ये सपोज यहां से ग्रो करना शुरू हुआ, करता करता यहां पहुंचा, ये यहां से ग्रो शुरू हुआ यहां पहुंचा, यहां जब ये दोनों पहुंचे तो टकरा गए। व्हेन दिस कोलिजन टेक्स प्लेस द क्रिस्टलाइन स्ट्रक्चर इज लॉस्ट। तो कॉम्पोजिशन मटेरियल तो वही है जो ग्रेन का है, फर्क ये है कि जहां ग्रेन के अंदर एक खास क्रिस्टल स्ट्रक्चर ऑर्गेनाइज्ड वे में अपीयर कर रहा है, ग्रेन बाउंड्री क्योंकि एरिया ऑफ मिसमैच है, एरिया ऑफ कोलिजन है, वहां एटम्स तो बेचारे उन्हीं कॉन्स्टिट्यूएंट्स के हैं लेकिन अब किसी खास क्रिस्टल स्ट्रक्चर में नहीं है, तो हम कहते हैं सर वो अमॉर्फस जगह हो गई है, दैट्स एन अमॉर्फस रीजन। आई होप मानव दैट इज क्लियर। So students, okay, thank you so much. We are left with about 2-4 minutes more. I will take you to the next slides tomorrow, but if there are any specific queries, you can ask me right away. I'll try to answer. Otherwise, I'll assume कि भाई चीजें सबको clear हो चुकी हैं. Are the things clear, students? ओके, लेट मी शो वन मोर स्लाइड। ये देखिए, ये अब ये पहला जो मैं ए में दिखा रहा हूं आपको माइक्रोस्ट्रक्चर किसी मटेरियल का, इसमें एक ही फेज है। दिस इंटायर ग्रे रीजन, लाइट ग्रे रीजन और ऑफ वाइट रीजन इज सम पर्टिकुलर फेज, एंड दिस इज इट। इस मटेरियल में और कोई फेज नहीं है, सो इट्स ए सिंगल फेज मेटेलिक सिस्टम। और ये इसके ग्रेन्स हैं 1 2 3 4 5 6, और ये सारी ब्लैक वाली इसकी ग्रेन बाउंड्रीज है। अब इसमें ये भी नहीं अज्यूम करने लग पड़ना कि ग्रेन बाउंड्री हमेशा ब्लैक ही होती है। इट कैन बी ऑफ एनी कलर, फेज कैन बी ऑफ एनी कलर, डिपेंड अपॉन कौन सा मटेरियल है, कौन सा फेज बना है, और इंपॉर्टेंटली आपने किस केमिकल से उसको एच किया है। हो सकता है सेम फेज है, जैसे मैंने पिछला आपको ये डायग्राम दिखाया, अगर ये मैंने सपोज नाइटल नाम का एक रिएजेंट है, केमिकल है, उससे एच किए हैं, अगर आप केलर्स एजेंट से कर देंगे तो ये कलर कुछ और आ जाएंगे दोनों फेजेस के, राइट। तो okay students, so we'll continue tomorrow. I hope you enjoyed this session. I enjoyed it thoroughly. Thank you for watching. Thanks for your time. Bye.